the next chapter in 10th standard is chapter 8 real numbers. In some states it could be chapter 5 or 10, okay, but the syllabus will be same. Now before understanding what are real numbers, let us understand what are natural numbers. We already know you have studied in your previous classes what are natural numbers. So natural numbers are nothing but they are this set of numbers 1 2 3 4 5 and so on. So these are natural numbers, and natural numbers are denoted by letter n. Now what are whole numbers? Whole numbers are nothing but all these numbers included plus 0. So whole numbers are 0, 1, 2, 3, 4, 5 and so on. So and whole number is denoted by the letter W. Okay. Now what are integers? Integers are nothing but all these numbers included plus negative numbers. So that integers are 0, 1, 2, 3, 4, 5 and so on, and also it includes negative numbers -1, -2, -3 and so on. So these are integers, and integers are denoted by Z. Okay. Now what are rational numbers? So rational numbers are denoted by letter Q. Rational number is any number which can be written in the form of P by Q. So where P and Q are integers and Q not equal to 0. Now according to this definition, rational number also includes set of integers. All integers are also rational numbers. Okay. Now integers are -3, -2, -1, 0, 1, 2, 3, 4, 5, right? So 5 is an integer. 5 can also be written as 5 by 1. Therefore 5 is a rational number also. Similarly -3 is an integer. So -3 can also be written as -3 means -3 by 1. So again now you can see this is in the form of P by Q. So this is also a rational number. So rational number includes all integers and also it includes other number also. For example, consider 1 by 2. 1 by 2 is also rational number because it is in the form of P by Q. P is an integer, Q also is an integer, and Q is not equal to 0. Now consider another number 5 by 3. 5 by 3 is also a rational number. Take 10 by 7. 10 by 7 also is a rational number. So 1 by 2, 5 by 3, 10 by 7, they are all in the form of P by Q, where P, that is the numerator, numerator and denominator both are integers, and denominator is not equal to 0. So rational number is any number which can be written in the form of P by Q, where P and Q both are integers and Q not is equal to 0. Rational number also includes integers. So I'll write that sentence also so that it's easy to understand. Rational number also include integers. Okay. Now to give a better understanding, I'll draw one diagram. Now I'll write a circle and see here I'll write n. N means it's a rational natural number. Okay. N consists of 1, 2, 3, 4, 5, and if you add 0 into that, it becomes whole number. Whole number consists of all natural numbers plus 0, and if you add negative numbers also to that, it becomes integers. Okay, it becomes integers. So integers is denoted by Z, and rational number are nothing but any number which is in the form of p by q, where p and q both are integer and q not is equal to 0. So natural number also contains integers, that is q. Okay, now what are irrational numbers? Irrational numbers are different. It doesn't include all these numbers. Irrational numbers are, they are separate numbers. Okay, irrational numbers are numbers. Irrational number is denoted by p. So irrational number are numbers which like root 2, root 3, root 5, 2 plus root 3. Now what is the speciality of irrational numbers? So irrational number is denoted by p. Now to understand what are irrational number, you need to understand what are rational numbers actually. See, rational numbers are any number which is in the form of p by q, right? P by q and p by q both are integers and q not is equal to 0. Now going by this definition, what is 1 by 2? 1 by 2 is a rational number. So when you divide 1 by 2, I will get 0.5. Okay, and what is 5 by 2? 5 by 2 is 2 to the 4. I will get 2.5. Okay, what is the value of 10 by 4? So 10 by 4 is a rational number. If I divide here, I will get 2.5. What is the value of 10 by 3? 10 by 3 is also a rational number. If I divide this one, I will get 3 3s are 9 decimal, then I will take 1 0, 1 is, then again 3 3s are 9, 3 3s are 9, like this I will get. So 0.3 will be recurring. The answer is 3.3 recurring. So in a rational number, the decimal is terminating. See, in the first 3 cases, decimal got terminated. It is 0.5. It is 2.5 here. Here also it is 2.5. In the last case, the decimal is not recurring. It keeps on going. 3.333, it keeps on going. So in a rational number, the decimal is terminating or it is recurring. But in irrational number, it is not so. So these are rational numbers. So but in irrational number, it's different. Irrational number. See, in irrational number, root 2, the value of root 2 is 1.4142135. It keeps on going, and the decimal will not terminate or it won't recur also. It's neither recurring nor terminating. And take for example root 5. If you take root 5, here also the value is 2.236067. It keeps on going. It never ends. Here also the decimal is never ending, and the decimal doesn't recur also. Consider another example. For example, 2 plus root 3. The value of 2 plus root 3 also, it is not terminating. The value is 3.7320508007. It keeps on going. So the decimal value will not terminate, also it won't recur. Though these are all irrational numbers. So now you got what the idea of natural numbers, whole numbers, integers, rational number, and also you got the idea of what is irrational number. Irrational number is represented by letter P. Now if you include all these numbers, then all those numbers included are called real numbers. Okay, real numbers are denoted by letter Z. Okay, real numbers is nothing but is a set of all rational and irrational numbers. All rational and irrational numbers. Irrational number. Okay. So rational number already includes natural number, whole number, and integers. Okay. This irrational number plus irrational number. Sorry, rational number plus all irrational numbers together clubbed are real numbers. The next topic in this chapter is Euclid's division lemma. See here, I'll give you some examples. Now consider this equation: 17 is equal to 6 into 2 plus 5. So how will I get this one? If I divide 17 by 6, 6 2s are 12. So I'll get remainder 5. 2 is the quotient. So I can write 17 is equal to 6 into quotient plus remainder 5. Similarly, I can write 5 is equal to 12 into 0 plus 5. So 5 is not divisible by 12. Okay. And that's how it is 12 into 0 plus 5. Now 20 is equal to 4 into 5 plus 0. If you divide 20 by 4, 4 5s are 20. Quotient is 5, remainder is 0. So I can write 4 into 5 plus 0. So in general, okay, if this number, if I consider as A, and if this number, if I consider as B, and this all this as Q. So here Q stands for quotient, and this is remainder. Okay, so I can write A is equal to B into Q plus R. A is equal to BQ plus R, where A and B are positive integers. Okay, and R actually R will be greater than or equal to 0, but it will be less than B only. Okay, R will be greater or equal to 0, but it will be less than B. So this is nothing but Euclid's division lemma. Now in the textbook they have given some examples. Can we do this one? So why don't you try finding integers Q and R for the following pairs of positive integers A and B. First example is 10, 3. So here if I divide 10 by 3, 3 3s are 9. Remainder is 1. So I can write 10 is equal to 3 into 3 plus 1. Here what is Q? Q is 3. Remainder R is 1. Okay. Second question. So here you can see it is 4, 19. 4, 19. So here if you divide 4 by 19, it's not divisible. 19 zeros are 0. 4 is the remainder. So I can write 4. I can write 4 is equal to 19 into 0 plus remainder is 4. So here Q is 3. R is 4. Okay. Now next sub question. So they are given 81, 3. So if I divide 81 by 3, 3 2s are 6. 2, I'll take 1. Now 3 7s are 21, right? 3 7s are 21. So and I'll get remainder 0. So 81 I can write as 81 is equal to 27 plus 27 into 3 plus 0. 0 is the remainder. So here this is 81 is equal to 3 into 27 plus 0. So here Q is 27 and R is 0. And in all the cases, this is A, this is B, this is A, this is B, this is A, this is B. So if you see the textbook, see Euclid's division lemma. Given positive integers A and B, there exist unique integers Q and R satisfying A is equal to BQ plus R, and R is between 0 and B. So This one already I have written here. This is nothing but Euclid division lemma. And Euclid's division lemma is used to find HCF of two numbers. Now let us go and solve some problems. So in the textbook already they are given some problems. Let us go through. So in the textbook you can see in example 1, use Euclid's algorithm to find the HCF of 4052 and 12576. See, finding HCF of small numbers is easy, but if there are big numbers like this, then we'll use Euclid's division lemma and find the HCF. So go through the procedure. All are easy, all are self-explanatory. There is another example here. Just go through it. All are self-explanatory, and there are similar problems in the exercise. So let us solve exercise problem. See, what is the normal procedure to find HCF? For example, we need to find the HCF of 32 and 8. So what is the normal procedure? Write all the factors of 32. 1 is a factor of 32. Then 2 16s are 32. 2 is a factor. Then 4 8s are 32. 4 is a factor of 32. Then 8 4s are 32. 8 is a factor of 32. Then 16 2s are 32. 16 is a factor. Then 32. All these are factors of 32. Okay. Factors of 32 are, okay. Then factors of 8 are, what is the factors? So 1 is a factor of 8, then 2 is a factor of 8, then 4 is a factor of 8, then 8 is a factor of 8. Among the factors, which is the common? Highest factor. See, 1 is common, then again 2 is common, 4 is common, but highest factor that is common is 8. Therefore, HCF of 32 and 8 is 8. So this is the normal procedure which we use to find HCF of two numbers. Take another example, 60 and 60. Factors of 60 are, okay, 16 and 18 I'll take, okay. What is the factors of 60? 1 is a factor, 230s are 60, then 320s are 60, then 4 is a factor, 4 15s is 60, then 5 is a factor, 5 12s are 60, then 6 is a factor, 6 10s are 60, 10 is a factor of 60, 10 6 are 60, then 12 is a factor, 12 5s are 60, then 15 is a factor, 15 to 4 is 60, then again 20 is a factor, 20 into 3 is 60, then 30 is also a factor, 30 into 2 is 60. So what are the factors of 18? So 1 is a factor, 2 9s are 18, 8 is a factor, then 3 6 are 18, 3 is a factor, then 4 is not a factor, 5 is not a factor, then 6 3s are 18, 6 is a factor, then 9 2s are 18, 9 is a factor, then after that 18 is a factor. So here also 16 is a factor, okay. See, 60 is a factor. Now among the factors here, what are the common factors? 1 is a common factor, 2 is a common factor, 3 is common factor, and 6, okay, and 6 is the highest common factor. Therefore HCF of 60 and 18 is 6. So this is the normal procedure which we follow to find the factors of two numbers, to find the HCF of two numbers. But what if the numbers are very big, like as shown in exercise 8.1? See here, 135 and 255, here 196 3820, okay. 196, 38220, and here 867 and 255. So if we go the normal procedure, we need to list all the factors, and it becomes a tedious process. So instead of that, we can use Euclid's division algorithm to find the HCF of two numbers. That one we'll do it now. Exercise 8.1, question number 1, sub question 1. Use the Euclid division algorithm to find the HCF of 135 and 225. So these are the two numbers. So I'll divide the greatest number by the smallest number. So 225 I'll divide by 135. Now 135 into 1 is 135. Now 5 minus 5 is 0. 12 minus 3 is 9. 0. So now I can write 225 is equal to 135 into 1 plus 90. Now this is nothing but Euclid's division lemma. Now I should find HCF. So still HCF it is not found. Now it's not complete. What I will do is, now again I'll take these two numbers and I'll write in the same fashion. Now I'll write 135. 135 is equal to 90. Now 135 I'll divide by 90. 90 ones are 90. So now 5 minus 0 is 5. 13 minus 9 is 4. So 135 I can write as 90 into 1 plus 45. Okay. Now again I'll take these two numbers. Now I'll write 90 is equal to 45. If I divide 90 by 45, 45 2s are 90 I'll get. So 45 into 2 plus 0 is 90. So if I get remainder 0, now R, this is R. If I get R is equal to 0, then this number whatever I'll get, this is the HCF. Okay. Therefore HCF of 135 and 225 is 45, or simply HCF of 135 comma 225 is equal to 45. Now sub question 2, the given numbers are 196 and 38220. Now I'll divide the greatest number by smallest number. 38220 divided by 196. So now 196 into 1 is 196. So now 12 minus 6 is 6. 17 minus 9 is 8. 2 minus 1 is 1. I'll take 2. Now 196. 196 into, like, I'll take 9. So 196 into 9 I'll get 6 9s are 54. If I carry 9 9s are 81. 81 86. Then 9 1s are 9. 10 17. So when I subtract 12 minus 4 is 8. 50 minus 6 is 9. So here 0 I'll get. So 980. Now if I multiply by 5, I'll get 5 6 are 30. 5 9s are 45. 5 9s are 45. 46 47 48. Then 5 1s are 5. 6 and 8 9. So 980 I'll get. So 38220 I can write as 196 into 195 plus 0. So here in the first step only I am getting remainder 0. Therefore I'll conclude this 196 as HCF. So HCF of HCF of 38220 and 196 is 190 196. Now third sub question is 867 and 255. So divide the greatest number by smallest number. 867 divided by 225. So this into 2, it's around 450. So I'll take 3. So 3 5s are 15, carry 1, 3 2s are 6 plus 1 7, 3 2s are 6, so plus 1, so this is 5, 255, okay, 3 5s are 15, carry 1, 3 5s are 15 plus 1 16, then 3 2s are 6 plus 1 7, 765. So if I subtract 7 minus 5 is 2, 6 minus 6 is 0, then 1. So 867 is equal to 255 into 3 plus 102. Now I'll consider these two. Now 255 is equal to 102. So I'll divide now. 255 divided by 102. So now if I take into 2, 2 2s are 4, 2 0s are 2 1s are 2. So I'll get 1 5 0. Okay, 255 I can write 102 into 2 plus 51. Now if I take these two, now 102 is equal to 51. Now it's clearly divisible. You can check it out. 102 divided by 51 is 2. 51 into 2 is 102. So 0 0. So 51 into 2 plus 0. Therefore remainder I am getting r is equal to 0 I am getting. Therefore this 51 is the HCF of 867 and 255. Therefore HCF of 867 comma 255 is equal to 51, and that completes problem 1. Exercise 8.1, question number 2. Show that any positive odd integer is of the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5, where q is some integer. Now what are positive odd numbers? So positive odd numbers are nothing but 1, 3, 5, 7, 9 and so on. Okay. Now according to Euclid's division lemma, if a and b are two integers, positive integers, then I can write a is equal to bq plus r, where q and r are also integers, and r varies between 0 and b. Okay. Now here let a be any positive odd number. So I'll in this given set I'll take a to be one positive odd number. Therefore I can write a is equal to 6q plus r. So you may be wondering why I am taking 6 only, 6q r. Why can't I take 2q plus r? Why I can't take 3q plus r? Yes, I can take, but for this problem I'll take 6q plus r only. Why I am taking? When I'll get the answer, you will come to know. And r can vary between 6 and 0. Okay. So now a I can also write as 6q plus 0. 6 cube plus 1. R can vary between 0 and 6. That's why I am writing like this. Yeah, I can write 6 cube plus 2. Also I can write 6 cube plus 3. Also I can write 6 cube plus 4. Also I can write 6 cube plus 5. So R can take all these possible values, right? Now, what are the multiples of 6? 6 ones are 6, 6 twos are 12, 6 threes are 18, 6 fours are 24. Now you can see, if you multiply 6 by any positive number, the result is positive even number. So the result is positive even number. Therefore, if R is equal to 0, I'll get even number only. Positive even number I will get. Because 6 into any number is even number. To an even number, if we add 0, we get even number only. But 6q is an even number. If we add 1 to it, we get odd number. Okay. And if R is 2, then we get positive even number. And for 6q, if we add 3, we get positive odd number. Again, 6q is an even number. To an even number, if we add another even number, that is 4, we get positive even number. For 6q is an even number, positive even number. For an even number, if we add odd number, that is 5, we get positive odd number. So now we are interested in odd numbers only. This. So that means whenever R takes value of 1, 3 and 5. Okay. Therefore, I'll write any positive odd number is given by 6q plus 1. So that is this thing, or 6q plus 3, or 6q plus 5. And that completes this problem. So similar problem they have given in worked examples. You can refer to that also. Even from worked examples also, you may get questions in examination. So go through worked examples from the text also. Exercise 8.1, question number 3. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So here contingent, army contingent members, contingent members are 616, and band members are 32. Now in a parade, first the band member will be in the front and the contingent members will be behind. They'll be doing march past in the parade, okay, in this direction, suppose say. Now we should arrange the band members in rows like this, okay. Also we should arrange the contingent members in rows like this. So we should arrange such a way that the number of columns in both should be same. So the number of columns should be the same. So this is very simple. So simply, if we find HCF of 616 and 32, we'll get the answer. So now these are big numbers. So in usual traditional way, we can't find the HCF. We should use Euclid's formula. So 616 I can write as 32. Now divide 616 by 32. 32 ones are 32. So 11 minus 2 is 9. Then 5 minus 3 is 2. I'll take this 6 here. Then 32 9s are, I'll get 288. So remainder is 8. So 616 I can write 32 into 19 plus 8. Now I'll take again consider these two numbers. Now 32 I can write 32 is equal to 8 into, now 32 if I divide by 8, it is divisible by 8. Okay, 8 fours are 32. So 8 into 4 plus 0. So if I 32, 8 fours are 32. Okay, remainder is 0. So 8 into 4 into 0. So here R I am getting 0. So therefore I can conclude that HCF is 8. Okay, this is HCF. Therefore HCF of 616 and 32 is 8. That means there should be number of columns is equal to 8. That means the band should have 8 columns, and also the contingent members should have 8 columns. Exercise 8.1, question number 4. Use Euclid's division lemma to show that the square of any positive integer is either of the form of 3m or 3m plus 1 for some integer m. So the given hint also, let x be any positive integer, then it is of the form of 3q and 3q plus 1 or 3q plus 2. Now square each of these and show that they can be written in the form of 3m or 3m plus 1. So according to Euclid's division lemma, okay, if a and b are two integers, then I can write a is equal to bq plus r, right, and r varies between b and 0. Okay, therefore if x is any positive integer, I can write x is equal to 3q plus r. Okay, where q and r are also integers. Now why 3q plus r only? I can take x is equal to 2q plus r, I can take x is equal to 10q plus r, I can take anything, it doesn't matter. But in this question I am taking 3q plus r only. Okay, I have reason for that. When I'll solve it, you will come to know why I have taken 3q plus r. So x is equal to 3q plus r, and r can vary between 3 and 0. So that means I can write x is equal to 3q plus 0, or I can write x is equal to 3q plus 1, or I can take 3q plus 2. Okay, I have 3 cases. Now in case 1, okay, that is x is equal to 3 cube. If I'll square both sides, so if I square both sides, I'll get x square is equal to 3q the whole square, that is x square is equal to 9q square I'll get. Okay, I'll write x square is equal to 3 into 3q into 3q only. 3q square is 3q into 3q. So I can write this as 3 into 3q square. So if I take 3q square as m, I can write 3m. Okay, I am just taking 3q square is equal to m. Okay, now in case 2, so in case 2, x is equal to 3q plus 1. Okay, now if I square both sides, what will happen? So x square is equal to 3q plus 1 the whole square I'll get. So x square, now expand it. So use the formula. What is the formula for a plus b the whole square is equal to a square plus b square plus 2ab. So this is 3q square plus 1 square plus 2 into 3q into 1 I'll get. So this is equal to 3q square plus 1 square is 1 plus 2 3 is a 6q I'll get. Okay, now I'll rearrange this 3q square plus 6q plus 1 I'll write. Now here again in first two terms I'll take 3 common. If I take 3 common, I'll get q square plus 6q plus 1. Now if I denote this as m, I'll get 3m plus 1. Okay, now in case 3, x is equal to 3q plus 2. Okay, now if I square both sides, I'll get what I'll get. X square is equal to 3q plus 2 the whole square. So x square is equal to, expand it now using the formula. So 3q the whole square plus 2 the whole square plus 2 into 3q into 2ab. Okay, so this is equal to 3q the whole square is, I'll write 3 okay, I'll take 3q into 3q. 3q the whole square is 3q into 3q plus 2 square is 4 plus 2 3s are 6, 6 2s are 12, 12q I'll get. Okay, now I'll rearrange this. I'll write 3q into 3q plus 12q plus 4 I'll write 3 plus 1 I'll write. Okay, now in the first 3 terms here I'll take 3q common. So 3 I'll take common. So the remaining is 3q square plus, if I take 3 common, I'll get here 4. I'll get 4q plus 1 this last one as it is. So now again if I take this part as m, I'll get 3m plus 1. Now you can see this and this are same only. Okay, so what it means, the square of any positive integer is either of the form of 3m. Okay, it's either of the form of 3m or 3m plus 1 or 3m plus 1, and that proves the problem. Exercise 8.1, question number 5. Use Euclid's division lemma to show that the cube of any positive integer is of the form of 9m plus 1 or 9m plus 8. So this question is similar to fourth question. Now according to Euclid division lemma, I can write, if a and b are two integers, I can write a is equal to bq plus r, where q and r also are integers, and r varies between 0 and b. Okay, now let x be any positive integer. Okay, and 3 also is a positive integer, so I can write x is equal to 3 cube plus r, and r can vary between 3 and 0. Okay, why I have taken here 3 only? Why not x is equal to 2 cube plus r? Why not x is equal to 19 cube plus r? I can take anything, it's not an issue. But for this question I will take x is equal to 3 cube plus r only. Why means, seeing the answer I got some hint, that's why when I'll solve the full question you will come to know. Okay, x is an integer, 3 is an integer, so I can write x is equal to 3 cube plus r according to Euclid's division lemma. So r varies between 0 and 3, that means x can be 3 cube plus 0, or it can be 3 cube plus 1, or it can be 3 cube plus 2. Now this is case 1, this is case 2, this is case 3. There are 3 cases depending upon the value of r. Now in case 1 r is equal to 0, therefore x is equal to 3 cube. Now I'll cube both sides. So if I cube both sides, what I'll get? X cube is equal to 3 cube the whole cube. So that means here 3q into 3q into 3q. So I'll get 27. Okay, 3 into 3 into 3 into q into q into q is q cube. Okay, here I'll take 3 3s are 9. 3 3s are 9. I'll take, and 3 q cube is left. Okay, now I'll take 9, and this I will write as m. Okay, now I'll stop here. Next I'll come to second case, case 2. So here x is equal to 3 cube plus 1 the whole cube. Now I'll cube both sides. So when I cube both sides, what will I get? X cube is equal to, sorry, this is x is equal to 3 cube plus 1. Okay, now if I cube both sides, I'll get 3 cube, x cube is equal to 3 cube plus 1 the whole cube. Now x cube is equal to, now expand 3 cube plus 1 the whole cube using formula. What is the formula for a plus b the whole cube? This is given by a cube plus b cube plus 3ab into a plus b. Now using that formula, expand this one, 3 cube the whole cube plus 1 cube plus 3ab. 3 a is 3 cube plus, sorry, 3 cube into 1 into a plus b, that is 3 cube plus 1. So this is equal to, now I'll get 27 q cube plus 1 cube is 1 only, plus 3 3s are 9 cube into 3 cube plus 1 I am getting. So here 27 q cube plus 1. So I'll expand this one, plus 9 q into 3 q. 9 3s are 27 q plus 9 q into 1 is 9 q only. Now this is equal to, now I will rearrange everything, 27 q cube. So plus, so this is 27 q square plus 27 q square plus 9 q plus 1 I will write, 1 I am taking at the end. Now here I will take 9 common factor. If I take 9 common factor, I will get 9 3 is 27, 3 q cube plus 9 3 is 27, q square plus q plus 1. Now this is equal to 9. If I consider this as m, so this is 9m plus 1. So I'll stop here. Now I'll take case 3. Case 3. In third case, x is equal to 3 cube plus 2. Now if I cube both sides, x cube is equal to 3 cube plus 2 the whole square. Now expand this, 3q the whole 3q the whole cube plus 2 cube plus 3 into ab, 3 into 3q into 2 into a plus b, 3q plus 2. So this is equal to 27 q cube. I will get 3 cube is 27, 3 into 3 into 3 plus 2 cube is 2 2s are 4, 4 2s are 8 plus, now here 3 3s are 9, 9 2s are 18, so 18q into 3q plus 2. Now I'll get 27q cube plus 8 plus, now if I open the bracket, okay, let it be as it is, 18q into 3q plus 2. I'll take this 8 at the end. Okay, now here if I take 9 common factor, so 9 3 is 27, 27q cube plus 2, here 9 2s are 18, so 2q into 3q plus 2 plus 8 I am getting. So here also I can take 9, this is again this, if I take as m, I can write 9m plus 8. So now you can see the cube of any positive integer is of the form of 9m, or it is of the form of 9m plus 1, or it is of the form of 9m plus 8, and that proves the problem, and that completes this exercise. Before going to next topic, let us see what are prime numbers and composite numbers. This one you already have idea of it, you have studied this in previous classes, and let us make a recap of it. Okay, now what are the factors of 2? Okay, factors of 2 are, okay, 1 and 2. So what are prime numbers? Prime numbers are numbers which has only 1 and itself as the factor. So 2 is a prime number. Now you take 3, number 3, this has factor 1 and 3, so even this is a prime number. But if you take 4, 4 is not a prime number, because 1 is a factor of 4, 2 is a factor of 4, and 4 is a factor of 4. Apart from 1 and itself, it has factor of 2 also. So by what is factor? Factor means it should divide the given number. So 2 divides 4, right? So apart from 1 and 4, 2 is also a factor of 4. Therefore 4 is not a prime number. 4 is a composite number. So 2 and 3 are prime numbers, 4 is a composite number. Now if I take 5, so factors of 5 are 1, 2 is not a factor, 2 doesn't divide 5, 3 doesn't divide 5, 2 is not a factor, 3 is not a factor, but 5 is a factor of 5. So this is a prime number, because only 1 and 5 is a factor. Now coming to number 6, so 1 is a factor of 6, then 2 is also a factor of 6, because 2 divides 6. And what about 3? 3 also divides 6, 3 2s are 6, and 6 is a factor of 6. Apart from 1 and 6, it has got 2 and 3 as factors. So this is not a prime number. All numbers which are not prime number will be a composite number. So what about 7? So factors of 7 are 1 and 7 only. It's not divisible by any other number. Therefore, this is a prime number. What about 8? Factors of 8 is 1, 2 and 4 is also a factor. 4 divides 8 and 8. So this is not a prime number. Therefore, this is a composite number. What about 9? So factors of 1 is 1. So 2 divides 2 is not a factor, but 3 divides 9, so 3 is a factor, and 9 is a factor. So apart from 1 and 9, 3 is a factor. Therefore this is not a prime, this is a composite number. What about 10? Factors of 10 are 1, 2 divides 10, so 2 is a factor. Then 5 divides 10, therefore 5 is a factor. Then 10, so this is also not a composite number, sorry, this is not a prime number. 10 is a composite number. What about 11? Factors of 11 are 1, 2 is 1 and 11 only. It doesn't get divided by any other number. So 1 is a prime number. So next is 12. 12 is a composite number because 1 divides, 2 also divides, and 3 also divides 12, and 4 also divides 12, 6 also divides 12, and 12 also divides 12. So this is a composite number. So 13 is a prime number because 1 and 13 are the factors. So this is a prime number. 14 is not a prime number. 1 divides 14, 2 divides 14, then 7 divides 14, and 14 divides. So this is a composite number. What about 15? 15 is not a prime number because 1 divides 15, then 3 divides 15, 5 divides 15, and 15. So this is a composite. What about 16? So 16, this is a composite number because 1 divides, 2 divides, then 8 divides, and 16 divides 16. So this is a composite number. What about 17? 17 is a prime number. 1 is a divisor of 17, and no other number except 1 and 17 are divisors of 17. Therefore 1 is a prime number. All numbers which are divisible by 1 and itself are prime numbers. The rest are all composite numbers. What about 18? 18 is not a prime number because 1 divides, 2 divides, then 3 divides, then 9 divides, and 18. This is a composite number. What about 19? So 19 is a prime number. So 1 and 19 only are divisors of 19. This is a prime numbers. So like this you can make a list of prime numbers and composite numbers. What about number 1? So number 1, this is neither composite neither prime. Okay. Not composite number. Why? Because to be a composite number it should have at least three factors. To be a prime number it should have at least 2 factors, that is 1 and itself. But here for 1 it has only 1 factor, that is 1. So therefore this is neither, 1 is neither prime number nor composite number. The next topic in this chapter is the fundamental theorem of arithmetic. I will explain you by giving you some practical examples. Now consider one number 6. Now 6 I can write 6. If I factorize 6, I will get, I can divide by 2. 2 3s are 6, then 3 1s are 3. So 6 I can write as 2 into 3. Now you can see 2 is a prime number, 3 is a prime number. And what about 6? 6 is a composite number. Okay. Now consider another number 30. So 30, if I factorize 30, so 30 is divisible by 2. So 2 1s are 2, 2 5s are 15. Again now 15 is divisible by 3. 3 5s are 15. Now 5 1s are 5. So 30 I can write as 2 into 3 into 5. Now you can see 2 is a prime number, 3 is a prime number, and 5 is a prime number. But 30 is a composite number. Now consider another example, 210. So 210 I can, if I factorize 210, so 2 10 is divisible by 2. 2 1s are 2, so 1 is not divisible, I'll put 0. Then 2 5s are 10. Now 105 is divisible by 5. 5 4s are 20, sorry, 5 2s are 10, 5 1s are 5. Now if I divide 21 is divisible by 7. 7 3s are 21. Now again 3 1s are 3. So 2 10 I can write 2 into 5 into 7 into 3. So I'll write in this order: 2 into 3 into 5 into 7. Now you can see 2 is a prime number, 3 is a prime number, 5 is a prime number, and 7 is a prime number. But 210 is a composite number. Now consider another example. 24. So 24, if I factorize 2 12s are 24, then 2 6 are 12, 2 3s are 6, then 3 1s are 3. So 24 I can write 2 into 2 into 2 into 3. So here prime number 2, it is occurring 3 times, so I can write 2 to the power of 3, 2 to the power of 3 into 3. Now consider another example. 45. So if I factorize 45, then it is divisible by 5. 5 9s are 45, then 3 1s are 3, 3 1s are, okay, 3 3s are 9, 3 1s are 3. Now 45 I can write as 3 into 3 into 5. So here 3, it is occurring 2 times, so 3 to the power of 2 into 5 I can write. Now 3 is a prime number, 5 is a prime number, and 45 is a composite number. So from this what we can conclude? We can write any composite number in terms of product of prime numbers, and that's what the fundamental theorem of arithmetic says. So if you see the definition in the textbook, the fundamental theorem of arithmetic says every composite number can be expressed, that means factorized, as a product of primes. So this is what I have done here. In the left hand side, all these are composite numbers. In the right hand side, all these are prime numbers. Every composite numbers can be expressed as a product of primes, and this factorization is unique. So these are unique. Now only see, for only 6 we can write 2 into 3. For no other number we can write the same way. So these are unique values, unique series, okay. And apart from the order in which the prime factor occurs. So it doesn't matter whether, for example, the last one is 3 to the power of 2 into 5. So this can also be written as 5 into 3 to the power of 2. So the order doesn't matter here, but every composite number can be expressed as a product of prime numbers, and this factorization is unique. So for no other number you will get 5 into 3 to the power of 2 except 45, okay. Similarly, for no other number you will get 2 into 3 into 5 into 7 except 210. So all these are unique for that composite numbers. So again in the textbook, if you see, there's an alternate definition for this. The prime factorization of a natural number is unique except for the order of its factor. That means if x is a composite number, we can express x in the form of product of prime numbers, that is p1 into p2 into p3, like this we can express up till pn. So x is composite number, and all these will be prime numbers. So in the textbook there is one example, so we will go through that example. Consider a number 4 to the power of n, where n is a natural number. Check whether there is any value of n for which 4 to the power of n ends with a digit 0. So example 5. So 4 to the power of n. So 4 to the power of n means n can be any number, any natural number. Natural number means 1, 2, 3, 4, 5 and so on. Now what is 4 to the power of 1? 4 to the power of 1 is 4 only. So this I can write 2 into 2, that is factors of 4 are 2. So now, or I'll write 2 to the power of 2. Now what is 4 to the power of 2? 4 to the power of 2 is 16. 16 is equal to 2 into 2. 2 2s are 4, 4 2s are 8. Then 8 2s are 16. So 2 to the power of, it becomes 2 to the power of 4. So now 4 to the power of 3 is 32. Sorry, 4 to the power of 3 is how much? 4 4s are 16. 16 4s are 64. Okay. 64 is how much? 64 also I can write 2 into 2 2s are 4, 4 2s are 8, 8 2s are 16, 16 2s are 32. That is 2 to the power of 5. So there is one more 2 here actually into, so it's 2 to the power of 6. Okay, so 4 to the power of generally I can write as 2 to the power of 2. 4 I can write 2 to the power of 2. So and n as it is. Now this again I can write as 2 to the power of 2 into n is 2n. So what it says, 4 to the power of n is equal to 2 to the power of 2n. So what is the meaning of this? That means only 2 is the factor of 4 to the power of, this is the meaning of this equation, this equality here. Okay, now the question is, what is the question? Check whether there is any value of n for which 4 to the power of n ends with a 0. So now 4 to the power of 1 is 4. So in 4 there is no 0 digit, I mean the n digit is not 0. Now 4 to the power of 2 is 16. So in 16 also there is no 0 in the units place, and 4 to the power of 3 is 64. So 64 also at the end there is no 0, but there could be some for some value of n there could be some digit like this x1 x2, and there could be a 0. And what is the value of n they are asking, or is there a 0 for some n value? That's the question they are asking. So if 4 to the power of n has a 0 in the units place, then it is divisible by 2, and also it is divisible by 5. Okay, divisible by 2 and divisible by 5. For example, 10 is divisible by 2 and 5. Again 100 is divisible by 2 and 5. 1000 also is divisible by 2 and 5. But here you can see here 4 to the power n is equal to 2 to the power of 2m. That means 2 is a factor of 4 to the power of n. That means 5 is not at all a factor. So that means 5 is not a factor of 4 to the power of n. That means there is no 0 in 4 to the power of n. So that means there is no natural number. There is no natural number n for which 4 to the power of n ends with a 0. So if it has to end with a 0, then that number should be divisible by 2 and 5 compulsorily, or that number should be should have factor as 2 and 5, but the given number has only 2 as a factor and not 5 as a factor. We can go through worked examples here. Example 6 and example 7 are all self-explanatory. Similar problems we have in the next coming exercise. So I'll be solving exercise problems. you go through this by yourself. Now exercise 8.2. Question number 1, express each number as a product of its prime factors. Sub question is 140. So what is prime number? Prime numbers are numbers which are divisible by 1 and itself only, and the rest all numbers are composite numbers. So here 140 is a composite number. We should express into product of prime numbers. So what we should do is, now 140 I should factorize. I'll divide by 2. So prime numbers are 2, 3, 5, 7 and so on. First I will go for the lowest prime number. Okay. Now 140 is divisible by 2. 2 sevens are 14. 2 zeros are 0. Then again it's divisible by 2. 2 threes are 6. 2 3s are 6. 2 5s are 10. Next, this is divisible by 5. 5 7s are 35. Okay. So 140 I can write 2 into 2 into 5 into 7, or 2 to the power of 2 into 5 into 7. So second sub question is 156. So 156, always go for the first, you check whether it is divisible by 2. 2 is the first prime number. First check with 2. If it is not divisible by 2, go for 3. Again, if it is not divisible by 3, go for 5. That way you can do. Now 2 sevens are 14. Then 2 8s are 16. Now again divide by 2. This is an even number, so it is divisible by 2. 2 3s are 6. 2 9s are 18. Now this is an odd number. It's not divisible by 2. I'll go for 3. 3 1s are 3. 3 3s are 9. So 13 is a prime number. It's not divisible by any other number. So what are prime numbers? Prime numbers are numbers which are divisible by 1 and itself only. So 156 is a composite number. I can now express this into product of prime numbers. That is 2 into 2. 2 is a prime number. Then 3 is a prime number. Then 13 is a prime number. So 2 to the power of 2 into 3 into 13. So next question, sub question is 3825. 3825. So factorize it. 3825. So this is an odd number which is not divisible by 2. So I can directly go and divide by 5. It may be divisible by 3. I don't know, but it definitely is divisible by 5. So I can go for 5. 5 7s are 35. Then 5 3 is remaining. 5 6 are 30. Then 2 is remaining. 5 5 are 25. Now again this is divisible by 5. 5 1s are 5. Then 2 is remaining. 5 5s are 25. Then 1 is remaining. Then 5 3s are 15. Okay. Now this is not divisible by 5 because this is an odd number. This is not divisible by 2 also. I'll check with 3. 3, yeah, it's divisible by 3. 3 5s are 15. Then 3 1s are 3. So now 15, again it's divisible by 3. 3 1s are 3. 3 7s are 21. Now 17 is a prime number. It's divisible by itself only. So 3825 can be written as, so I'll arrange in order. Okay. First I'll write as it is. This is 5 into 5 into 3 into 3 into 17. So I'll rearrange 3 into 3 into 5 into 5 into 17. So 3 to the power of 2 into 5 to the power of 2 into 17 is the answer. So you can leave the answer here only. It's not at all wrong. All these 3 steps are correct answer only. Now the next question, sub question is 5005. 5005. So it clearly we can see that it is divisible by 5. It's not divisible by 2. It may be divisible by 3, but I'll go for 5 only. 5 5 ones are 5, 0 0, 5 ones are 5. Now this is not 1001 is not divisible by 2. It's not divisible by 5 also. So 3 is divisible by 3. 3 3s are 9, then 3 3s are 9. It's not divisible by 3. It's not divisible by 5. 7, I'll check. 7 ones are 7. 3 is remaining. 7 4s are 28. 7 4s are 28. Then 2 is remaining. 7 3s are 21. Okay. Now 143. Now 143 is not divisible by 2. It's not divisible by 5. It's not divisible by 3 also. It's not divisible by 7 also. But it's divisible by 11. 11 ones are 11. 3 is remaining. Then 11 3s are 33. So 13 is a prime number. 13 ones are. So 5005 I can write as 5 into 7 into 11 into 13. So next sub question. So fifth question, 7429. 7429 I'll do. So it is not divisible by 2, it's not divisible by 5. I'll check with 3. 3 2s are 6, then 1 is remaining. 3 4s are 12, then 2 is remaining. Then 3 7s are 21. 3 7s are 21. 1 is remaining. So 1 now 19. 19 is not divisible by 3. So the next number. So this is not divisible by 3. It is not divisible by 5. It is not divisible by 7 also. 7429. So it is divisible by 17. Okay. 17 into 4. 17 4s are 68. So 68 means 6 is remaining. Then 17 into 3 and 17 into 7, it's divisible by 17. Then 437, this is divisible by 19. 19 2s are 42. 19 2s are 42. 1 is remaining. Sorry, 38. 19 2s are 38. 38 means 5 is remaining. 57. 13 3s are 19 3s are, I'll get 57. Okay. Now 23 also is a prime number. 23 ones are. So 7429 I can write as 17 into 19 into 23, and that completes this question number 1. Exercise 8.2, question number 2. Find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is equal to product of the two numbers. So first sub question is 26 and 91. So now I'll factorize 26. So I'll divide by prime numbers. So prime numbers are 2, 3, 5, 7, 11 and so on. So 26 is an even number. So divisible by 2. 2 ones are 2. 2 3s are 6. 13 is a prime number. 13 ones are 13. So 26 I can write as 26 is equal to 2 into 13. Now 91 I can write as, so 91 is divisible by 7. 7 ones are 7. 2 is remaining. 7 3s are 21. So 13 is a prime number. 13 ones are. So now 19 I can write as 7 into 13. Now in these two, the common number is 13, common factor. So 13 is a factor of 26. Also 13 is a factor of 91. And the So 13 is common factor between 26 and 91. Therefore HCF, what is HCF? Highest common factor. So highest common factor is 13. HCF of 26, 91 is equal to 13. Now what is the LCM? So LCM of 26, 91. So here LCM is equal to, so now take HCF is 13, okay, and here in the first in the factors of 26, apart from 13 what is left? 2 is left, so it multiply it by 2, and in the factors of 91, and in the factors of 91 apart from 13 what is left? 7 is left, so 13 into 2 into 7 will be the LCM. So 13 into 2 7s are 14, so 3 4s are 12, carry 1, 3 1s are 3 4, then 1 3s are 3, 1 1s are 1, 2, 172, oh this is 5, okay, so 182. So LCM of 26 and 91 is 182. Now if I do HCF of 26 91 and if I multiply HCF of 26 and 91 by LCM of 26 and 91, this should be equal to 26 into 91. So let us check it. So here LCM of HCF of 2691 is 13 and LCM of these two numbers is 182. So 26 into 91, so in both sides we will get 2366, 2366, 2366. So I am skipping multiplication here, you can check it. The next sub question is 510 and 92. So 510 I can write as, so 510 factorize it, so it is divisible by 5, 5 ones are 5, then 5 0, 5 twos are 10, then 102 is not divisible by 5, it is divisible by 2, 2 5s are 10, 2 1s are 2, 51 is divisible by 7, 7, sorry, it's divisible by 3, 3 1s are 3, 3 7s are 21, 17 is a prime number. So 510 I can write as 2 into 3 into 5 into 17. Okay, I have taken in ascending order of the prime numbers. Now 92 I can write as, I can divide by 2, 2 4s are 8, 2 6 are 12, then 2 1s are 2, 2 3s are 6, 13 1s are 13. So this I can write 2 into 2 into 13. Now highest common factor, so which is common here? Only 2 is common, no other factors are common. So highest common factor, so only highest common factor that left is 2. So HCF of these two numbers is equal to 2. Now what is LCM? LCM is equal to, now highest common factor is 2, then apart from 2 what is left here? 3 is left, then 5 is left, and 17 is left, multiply it. Now again coming back here in the next row, what is left apart from the common factor? 2 is left and 13 is left, 2 into 13. So you multiply all, you will get the LCM. So 2 3s are 6, 6 2s are 12, 12 5s are 60. So this is 60 into 17 into 13. So when you multiply, you will get 2 3 4 6 0. I have skipped the multiplication, you please check it out. Now I will multipy HCF and LCM. HCF into LCM. So if I multiply, I should get product of the numbers, that is 512. Given numbers are 512 and 92. So HCF of these two numbers is 2 and LCM is 23460. So this should be equal to 512 into 92. So please check it out. In the left hand side you will get 46920 and in the right hand side also you will get 46920. Exercise 8.2, question number 2, sub question 3. The given numbers are 336 and 54. So 336, so it is easily divisible by 3. 3 ones are 3, 3 ones are 3, 3 twos are 6. So you can divide with any prime number. It's not necessary to divide by 2 or 3 or 5, whatever. Whichever is divisible, you can go ahead and do it. Okay. So this is divisible by 3. I started with 3. 3 ones are 3, 3 ones are 3, 3 twos are 6. Now this is divisible by 2. 2 5s are 10, 2 6 are 12. Then 2 2s are 4. 2 2s are 4, 2 8s are 16. Then 2 1s are 2, 2 4s are 8. Then 2 7s are 14, 7 1s are. So 36 I can write as 2 into 2. How many 2? 1 2 3. 2 into 2 into 2. So 2 into 2 into 2. 1 2 3 4. 4 2s are there and 1 3 is there and 1 7 is there. So and what about 54? 54, factorize it. So if I factorize 54, 2 divisible by 2, 2 2s are 4, 2 7s are 14, which is divisible by 3, 3 9s are 27, again 3 3s are 9, 3 1s are 3. So this is equal to 2 into 3 into 3 into 3 I can write. So now among these two numbers we should find the common factors. One factor which is common is this one. 2 is a common factor and 1 3 also is common factor. This 3 also is common factor. So HCF means highest common factor. 336, 54. So here there are two factors which are common, so we should multiply those two. So 2 into 3, so is equal to 6. So HCF of these two numbers are is 6. Now LCM of 336 and 54 is, so you take the common factors here. Common factor is 2 and 3, that is 6. Take that HCF as it is into, now in the first row here what are the factors that are remaining? 2 into 2 into 2 into 7 is remaining. So 2 into 2 into 2 into 7 into, now in the second row here which is the common factor that is remaining? 3 and 3 into 3 into 3. So if you multiply all this, how much you will get? You will get 3024. You can please check it out. Now HCF of 336 and 54 into LCM of 336 54 should be equal to product of the numbers, that is 336 into 54. So this applies to any two numbers. Okay, product of HCF and LCM is equal to sum of those two numbers. So here I got 6 and this is 3024. If I multiply these two, so here right hand side 336 into 54. So in both the sides you will get 18144. 18144. So I have skipped multiplication. You please check it out. Exercise 8.2, question number 3, sub question 1. Find the LCM and HCF of the following integers by applying the prime factorization method. And the given numbers are 12, 15 and 24. So this problem is same as the previous problem, but here 3 numbers are given, that's it. So 12 I can write as, if I factorize, I'll get 2 6 are 12, 2 3 are 6, 3 1 are 3. So I can write 2 into 3, then 15. So 15, if I factorize, 3 5 are 15, 5 1 are 5. So 3 into 5, and 24. So 24, 2 12s are 24, 2 6 are 12, 2 3s are 6, 3 1s are 3. So this is equal to 2 into 2 into 2 into 3. Now what is the common factor in all these 3? Oh, the last number is 21, it's not 24. So 21 means 3 7s are 21. So 3 into 7. Okay, factors of 21 is 3 into 7. Now among these 3, which is the common one? 3 is common. Okay, 3 is the common factor. Okay, so HCF of 12, 15 and 21 is 3. Okay, and LCM of 12, 15 and 21 is equal to, now here 3 is the HCF which we have got. Now into, in the first row here, what is the factors left? That is 2 into 2. Again, now in the second row, what is the factors left? 5 is left. And in third row, what is the common factors left? That is 7. So 2 3s are 6, 6 2s are 12, 12 5s are 60, 60 into 7, 6 7s are 42. So 420 is the LCM. This I am striking out. Exercise 8.2, question number 3, sub question 2. The given numbers are 17, 23 and 29. So 17 itself is a prime number. So 17 I'll write as it is. Then 23 also is a prime number. And 29 also is a prime number. So highest common factor. So now 17 I can write as 17 into 1, 23 I can write as 23 into 1, and 29 I can write as 29 into 1. Now highest common factor. So only this is the common among these 3. So HCF is 1. Okay, now LCM of 17, 23, 29 is equal to, so 1 as it is, HCF into the first row what is remaining is 17, the second row 23 is remaining, and here 29. So now 17 into 23 into 29 is equal to 11330. So it's 9, 11339. I've skipped the multiplication step, you can verify it. And the last sub question in this question number 3 is, given numbers are 8, 9 and 25. So 8 I can write as 2 into 2 into 2, 2 2s are 4, 2s are 8. So just do it, 2 4s are 8, 2 2s are 4, 2 1s are 2. Now 9. So 9 is 3 into 3. Okay, 3 3s are 9. What about 25? 5 5s are. So what is the common factor here? Nothing. So into 1 is the common factor. Okay, see, 1 is also a factor. 1 is a factor of 8, 9 is a 1 is a factor of 9, and 25 is a factor, 1 is a factor of 25 also. Therefore HCF, highest common factor. So among all the factors, which factor is common? 1 is the common one, highest common factor. So highest common factor is 1. Now LCM is given by 1. HF, write the HF as it is. Now the first row, what is left? 2 into 2 into 2 is left, into the second row 3 into 3 is left, and in the third row 5 into 5 is left. So what is the LCM now? 2 2s are 4, 4 2s are 8, into 3 3s are 9, into 5 5s are 25. If you multiply everything, you will get 1800. So LCM of these three numbers is 1800. HCF is 1, and that completes this problem. Exercise 8.2, question number 4. Given that HCF of 306 and 657 is 9. So we should find the LCM of 306 comma 657. So always HCF of A comma B into LCM of A comma B is equal to A into B. So this is true for all. Okay. Now HCF of 306 657, so into LCM of 306 657 is equal to 306 into 657. Okay. Therefore now HCF it is given as 9. So 9 into LCM of 306 657 is equal to 306 into 657. Therefore LCM of 306 657 is equal to 306 into 657 divided by 9. I am bringing this 9 which is there in the left hand side to the right hand side. If I bring it to the right hand side, it will come to the denominator. So 3 3s are 9, 3 1s are 3, 0, 3 2s are 6. Now again it is divisible by 3. 3 1s are 3, 3 3s are 9, 3 4s are 12. It is divisible. So I am left with 34 into 657. So 34 into 657, you will get 22338. Please check the answer. I have skipped the multiplication, and that completes this question. Exercise 8.2, question number 5. Check whether 6 to the power of n can end with the digit 0 for any natural number. So given number is 6 to the power of n. See, for any number to end with 0, it will be divisible by 2, and it will also be divisible by 5. For example, 10, it is divisible by 2 and 5. Okay. What about 100? 100 also is divisible by 2 and 5. For example, 20 also is divisible by 2 and 5. For example, 400 is also divisible by 2 and 5. So now 6 power of n I will write as, so 6 I can write as 2 into 3. So 6 power of n I can write as 2 into 3 to the power of n. So 6 power of n, so 2 into 3 to the power of n means 2 to the power of n into 3 to the power of n. So what this equation says is 2 and 3 are factors of 6 power of n. Okay. Therefore 2 and 3 are factors of 6 power of n, but 5 is not a factor of 6 power n. Okay. But 5 is not a factor of 6 power of n. So as I told you here, if both 2 and 5 are divisible by if the number is divisible by both 2 and 5, only then the number ends with 0. So but here 5 is not at all factor, only 2 and 3 are factors. Therefore we can conclude that 6 to the power of n does not end with 0 for any value of n. No matter what the value of n, 6 power of n does not end with 0. Okay, for example, we can check. For example, 6 power of 1 is 6 only. What is 6 power of 2? 36. What is 6 power of 3? 36 into 6. So 6 6 are 36, 6 3 are 18, 19, 20, 21. Is it correct? Yes, it's correct. See, now everywhere you can see the number doesn't end with 0 at all. Like this you can go on listing, but in no number you get 0, which is at the unit place. Exercise 8.2, question number 6. Explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. So first one is 7 into 11 into 13 plus 13. So what is this equal to? 7 into 11 is 77. 77 into 13. 3 7s are 21. 3 7s are 21, 22, 23. Then 1 7s are 7. 1 7s are 7. 1 7 8 9 10. Carry 1. 7 8 9 10. So 101. 101 plus 13. 101 plus 13. How much? 4 1 0 1. So this is equal to 1014. Now if we take the factors of 1014, what is the fact? 1014. So this is an even number, easily divisible by 2. 2 5s are 10. Then 1 is not divisible, I'll put 0. Then 2 7s are 14. Then 5 not 7. It's not divisible by 2. We'll try in 3. 3 1s are 3. Then 2 is remaining. Then 3 6 are 18. Then 2 is remaining. Then 3 9s are 27. Okay. Now 169. This is divisible by only 13 only. 13 into 13 is 169. So 1014 is equal to 2 into 3 into 13 into 13. So there are how many? More than 3 factors, okay, for this number. Therefore this is a 1014 is a composite number. So what are composite numbers? Numbers for which there are more than 3 factors. If there are only 2 factors, then it's a prime number. Okay. Now second one is 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. So here 1 2s are 2 2 2 3s are 6 6 4s are 24. So from here to here I'll get 24. So 24 into, then 6 5s are 30. This is 30. This is 7 plus 5. So now 30 into 24 is 4004. 3s are 12. Then 20002. 3s are 6. So 0 2 6 plus 1 7. So this into 7. 7 0 0 7 2s are 14. 7 7s are 49 plus 1 50. So this 5040 plus, if I add 5, I'll get 5045. So this is equal to 5045. Now if I check the factors of 5045, so this is divisible by 5, so 5 ones are 5, then 0, so again 0, 4 is not divisible, again I'll put one more 0, 45 I'll get 5 nines are 45, then see 1009 is actually a prime number. 1009 is divisible by 1009 only. Okay, so now 5045 I can write as 5 into 1009. So it means 5 is one factor of 5045, and 1009 also is a factor of 5045. And also apart from this, what are the other factors? So that factors of 5045 are one is a factor, okay, and here as we derived 5 is a factor, then 1009 is a factor, and also 5045 is a factor. So altogether there are 4 factors for 5045. So this is a composite number. If it were a prime number, only 1 and the number, if a given number has factor 1 and itself, then it's a prime number. So here there are 4 numbers which are factors of 5045. Therefore 4045 is a composite number. That ends this one. Exercise 8.2, question number 7. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field. Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? So there is a circular sports field, and Sonia takes 18 minutes, okay, to drive one round like this. Okay, so Sonia takes 18 minutes and Ravi takes 12 minutes for the same. Okay, if Ravi also starts from here, Ravi takes only how much? 12 minutes. So Ravi will take 12 minutes to complete this round. So but the circular path distance is same only, both whatever they are covering the distance, that is same for both. Okay, but just for indication type I have written 2 circles there. Now if both will start, at what time will they meet at the starting point? That's the question. So now for this to find, I'll factorize 18 and 12. Sorry, Ravi is taking 12 minutes to drive one round. Okay, so factors of 18 are, so 18 I can factorize, 2 9s are 18, then 3 3s are 9, 3 1s are 3. So 18 I can write 2 into 3 into 3. Now 12 if I factorize, 2 6 are 12, then 3 2s are 6. So 12 I can write as 2 into 3. Now if I find the LCM of these two numbers, I'll get where those two people will meet. Okay, now LCM of 18 and 12 is equal to, now here first what is the common factors? 2 is a common factor, again 3 is a common factor. So first write that one, 2 is a common factor, 3 is a common factor, and now write the remaining. So in the first row 3 is remaining, again in the second row 2 is remaining. So 2 3s are 6, 6 2 3s are 6, 6 3s are 18, 18 2s are 36, so 36. So LCM of 18 and 12 is 36. That means after, if both start at the same point and they go circular in that field, then at 36th minute they both will meet. So actually if you see, Sonia will put 2 rounds, 18 2s are 36, okay, 18 2s are 36. So Sonia will put 2 rounds, and 12 3s are 36. So and Ravi will put 3 rounds, and at the starting point, they will meet again, and at 36th minute. The next topic in your chapter is irrational number. So before understanding what are irrational number, we should know what are rational numbers. So rational numbers, so numbers which can be represented in the form of p by q, where both p and q are integers and q not equal to 0. So all numbers which can be represented in this way are called rational number. For example, 1 by 2. So 1 by 2 is a rational number because 1 is an integer, 2 is an integer. And suppose if you take the decimal equivalent of this one, what will you get? You will get 0.5. Now what is 3 is a rational number, because 3 I can write as 3 by 1, okay, 3 I can write as 3 by 1. So the decimal equivalent of this one is 3.00. And 10 by 4 is a rational number. So what is the decimal equivalent? If I divide 10 by 4, 4 2s are 8, then 4 5s are 20, so I'll get 2.5. Now for example, 10 by 3 is a rational number because 10 is a integer, 3 is an integer. Now if I evaluate this one, I'll get 3.333. So 3.3 is recurring. I can write as 3.3 like this, bar dash. So 3.3. So 0.3 is recurring. So in all rational number, there is one important thing that we should notice, that the decimal equivalent of the rational number is terminating. See here it is 0.5, it stopped there itself. Here 3.0, it stopped there itself. Here it 2.5, it stopped there itself. So here in the third case, it started recurring. The value is 3.3333. So 0.3 is recurring. Or in other words, we say the last case as non-terminating repeating. Here 0.3, that is repeating. 0.3 is repeating. But in irrational number, it's not like this. For example, root 2 is an irrational number. If you take the decimal equivalent of this one, it is, so let us evaluate the value of root 2. How to evaluate root 2? So you should divide by some number. Now I'll take 1. So 1 1s are 1, I'll take. So now 2 minus 1 is 1, I'll get. Now I'll add 1 to this one. So 1 plus 1 is 2. Now I'll take one decimal point, put 2 zeros. Now 2 4s are 24 into 4. So 24 into 4, I'll get 96. So 100 minus 96 is 4. Now here I'll add 4 to this 24 plus 4, I'll get 28. Now already I had put a decimal point there, so I can put 2 zeros again. So now if I take 1, 281 into 1 is 281. I can't take 2. 281 into 2, if I do, it will exceed 400. So I'll take 281. So like this, I can go on evaluating the value of root 2. Actually, the value of root 2 will be 1.4142135 and it will never end. It won't recur also and it won't terminate also. That's the speciality of irrational number. In rational number, the decimal equivalent will terminate or it will recur. But here it's not like that. It's non-terminating and non-repeating. Okay. Now, if you take the if you evaluate the value of root 3, how to evaluate root 3? So 3 now I'll divide by 1, 1 ones are 1. So I'll add the same one here, 1 plus 1 2. Here 3 minus 1 is 2. Now I'll put one decimal point. I'll take 2 zeros. Now 27 into 7 I'll get 189. If I take 28 into 8, it will exceed 200. That's why I've taken 7 only. 27 into 7, 189. So 200 minus 189 is 11. So for this 27, I'll add 7 on 7. So 343 I'll get. Now like this I can go on. Now 3. Okay, 343 into 3. I'll take 2 zeros here. I'll get 1029. Okay, so like this I can go on evaluating the value of root 3. So the value of root 3 is 1.73205080. So here also the decimal equivalent of root 3 is not terminating. Also it is not recurring. So similarly, if you take if you evaluate value of root 5, the value of root 5 is also not terminating or it is not recurring also. So 2.236067977 like this it goes on. So in rational number the decimal equivalent is terminating or it is recurring, but in irrational number the decimal equivalent is not terminating, also it is not recurring. That is the main feature of irrational number. Now if you add rational number into rational number and then irrational number, what will you get? So if you add rational number plus irrational number, you will get irrational number only. So for example, root 2 is a rational number, okay, and 2 is a rational number. If you add these two, you will get irrational number only. So value of root 2 is, just now we saw it is 1.41422135. Okay, 2 is just 2. Okay, if you add, you will get 3.41422135, and okay, this is an irrational number. Similarly, if you add 1 plus root 3, root 3 is an irrational number. So what is root 3? We came to know it is 1.73205080, and it is not terminating. So if you add these two numbers, so it is 2.73205080. So for an irrational number, if you add a rational number, the result is irrational number. Also, rational number into irrational number, what could be the value of this one? This also will be irrational number only. Irrational number. For example, if you multiply 2 into root 2, so root 2 is 1.41421356. Okay, and it is not terminating. So when you multiply, you will get 2.8284271 like this, and it's not terminating, also it's not recurring. So this is also irrational number. So similarly, if you multiply 2 into root 3, so 2 into root 3 is 2 into what is root 3? Root 3 is 1.73205080, and it is recurring. You will get 3.46410.161, and it is recurring. Sorry, it's not terminating also, it is not recurring. And also, if you divide irrational number by a rational number, so you will get irrational number only. Irrational number. So based on this concept, let us go ahead and see what's there in your textbook. There will be some solved problems and also some exercise problems will be there. Let us proceed and see what's there. As I told you, all these numbers are irrational numbers: root 2, root 3, root 15, pi, root 2 by root 3. See, root 2 is a irrational number, root 3 also an irrational number. Sometimes irrational number divided by an irrational number is a irrational number. Sometimes it may be rational number also. Okay. Next is 0.101110, 1110, 111110, etc. All these are rational numbers. Next topic is Theorem 8.3. The statement of Theorem 8.3 is like this: let P be a prime number if P divides A square, then P divides A, where A is a positive integer. So the proof is like this. So if I factorize A is a integer. Now what are the factors of 6? 6 I can write as 2 into 3, 2 3s are 6, 2 and 3 are factors of 6. And what are the factors of 10? So I can write as 2 into 5, 2 and 5 are the factors of 10, right? What are now 12? I can write as 2 into 3 into 2, or 2 square into 3 is 12. So that means 2 and 3 are factors of 12. Now if A is an integer and if I factorize it, I can write as P1 into P2 into P3 up till Pn, where P1, P2, P3 are all factors of A. Now if I square both sides of the above equation, I will get A square is equal to P1 into P2 into P3 up till Pn, the whole square. So or A square is equal to P1 into P1 square into P2 square into P3 square up till Pn square. Now given that P is a prime number and it divides A. Okay, given that P divides A square, therefore P is part of 1. Okay, so this I'll write as 1. So given that P divides A square, therefore P should be part of 1. But the factors of A are P1, P2, P3 up till Pn. Therefore P is one of the factors of A. This is according to the uniqueness of fundamental theorem of arithmetics. And that completes this theorem. The next topic is theorem number 8.4. So it says root 2 is irrational number. So proof. So in proof what I will do is I will assume root 2 is a rational number and I will try to prove it. If I am not able to prove it, then root 2 is irrational number only. So I will assume that root 2 is a rational number. So let root 2 be a rational number. So if it is rational number, then it can be expressed in the form of p by q, right? So I'll put it as r by s. So what is rational number? Rational number is any number which is in the form of p by q, where both p and q are integers and q not equal to 0. So here, since root 2 is rational number, I can equate it to r by s. Now, any integer can be written as product of prime numbers. For example, 8 I can write as 2 into 2 into 2, right? And 4 I can write 2 into 2. Now if I divide 8 and 4, what will I get? So here common factors will get cancelled and I will be left with something which has no common factor. Okay, so 8 by 4 is nothing but 2 by 1. So here also r will have some common factor and s also will have some common factor. If I cancel all those common factor, I will be left with a and b, where a and b will not have any common factor. Okay, a comma b will have no common factor because I have cancelled. Okay, just as in this case, after cancelling I will get r by s becomes a by b. Now I will square both sides. Okay, I will cross multiply and square. Okay, cross multiply and square both sides. So if I cross multiply, it becomes b into root 2 is equal to a. After then if I square it, b into root 2 the whole square is equal to a square. So this is equal to b square into root 2 the whole square is equal to a square. So this is equal to b square. Root 2 into root 2 the whole square is 2 only. So this is equal to a square. Now this one I will mark as equation 1. Okay, now this one I will mark as equation 2. See, in equation 1 says that a and b have no common factor. Okay, now according to equation 2 is a factor of a square. For example, if I write 2 into 3 is equal to 6, what it means? 2 and 3 are factors of 6. Okay, if I write 2 into 5 is equal to 10, so this means 2 is a factor of 10, also 5 is a factor of 10. Therefore here b square into 2 is equal to a square. That means 2 is a factor of a square or 2. Okay, therefore 2 is a factor of a square. So according to theorem number 8.3, 2 is also a factor of a. But what equation 1 says? A and b have no factor. But 2 says a square as factor. Equation 2 says 2 is a factor of a. Both are contradictory. Okay, so this contradicts equation 1. So which is contradicting? Equation 2. Equation 2 is contradicting equation 1. So equation 2 says 2 is the factor of a square, but equation 1 says a has no factor. So this contradicts equation 1, which says that a and b have no common factor. So why this is happening means our first assumption that root 2 is a rational number, that assumption itself is wrong. Okay, therefore our assumption that root 2 is a rational number is wrong. Therefore root 2 is an irrational number. So I tried to prove that root 2 is a rational number, but I am unable to do that. So what it means, root 2 is a rational number, and that completes the proof. So the next topic is example 9. So prove that root 3 is irrational. Okay. So to prove root 3 is irrational number. So here also I'll use the same way that I used to prove that root 2 is irrational number. So in the previous case I tried to prove root 2 is an rational number, and I was not able to do so. So here also I'll try to prove that root 3 is an rational number. Okay, let root 3 be a rational number. So if it is, what are rational number? Rational number are numbers which is in the form of p by q, where p and q are integers and q not equal to 0. Therefore root 3 I can write as r by s, where r and s are integers and s is not equal to 0. Now r and s will have some common factor which I can cancel. For example, as in the previous case, 8 by 2, if I have 8 by 4, 8 I can write as 2 into 2 into 2, and 4 I can write 2 into 2. So 2 will get cancelled. So 8 by 4 is equal to 2 by 1. So here only, if I cancel the common factors, root 3 I can write as a by b. Okay, so now a and b has no common factor because I have cancelled it. Okay, so this I will mark equation 1. Now squaring I'll cross multiply and square both sides. So if I cross multiply, b into root 3 is equal to a, I'll get. Squaring both sides, what will I get? B square into root 3 the whole square is equal to a square, I'll get. So b square into root 3 the whole square is just 3. Okay, is equal to a square. So this I'll mark as equation 2. So from equation 2 what it says is 3 is a factor of a square. For example, 2 into 3 is equal to 6. That means 2 is a factor of 6 and 3 is a factor of 6. So that means here 3 is a factor of a square. So therefore 3 is a factor of a also, according to theorem 8.3. But this contradicts equation 1. See, according to equation 1, a and b has no factor because we have cancelled it. Okay, this contradicts equation 1, which says that a and b have no common factor. Therefore our assumption assumption that root 3, see in the first line only I assume that root 3 is an rational number, so that assumption itself is wrong. That's why we got contradictory equations. So therefore our assumption that root 3 is a rational number is wrong. So that means I am unable to prove that it's a rational number. Therefore its root 3 must be a irrational number. Therefore root 3 is an irrational number, and that completes the proof. So the next topic is example 10. Show that 5 minus root 3 is irrational. Example 10. Show that 5 minus root 3 is irrational. So here also, as in the previous case, we will try to prove that this number is an rational number. So if you are unable to prove that if this is a rational number, then it means it's an irrational number. So what I'll do is, I'll assume let 5 minus root 3 be a rational number. So what are rational numbers? Rational numbers are in the form of p by q, where p and q both are integers and q is not equal to 0. Therefore 5 minus root 3 is equal to r by s. Now r and s will have some common factor which I will cancel, and I will get a by b. So for example, as in the previous case, 8 by 4 is 2 into 2 into 2 by 4 is 2 into 2. So here common factors will get cancelled. I will be left with 2 by 1. 8 by 4 is equal to 2 by 1. So here r and s will have some common factors. After dividing, I will be left with a by b, and a by b have no common factor. So a comma b has no common factor. I'll mark this as equation 1. Now I will rearrange this one. 5 minus a by b is equal to root 3. I brought a by b to the left hand side and took root 3 to the right hand side. Now you can see that 5 is a rational number. Okay, this is a rational number, and a by b also is a rational number. But root 3 is an irrational number. We already proved in the previous page. Okay, in example 9 we already proved that root 3 is an irrational number. So how it is possible? See, rational number minus rational number. 5 is a rational number. A by b is a rational number. If we subtract two rational number, the result is a rational number. But in the right hand side we are getting, but in the right hand side it is an irrational number, which is not possible. So where we went wrong? So I am writing left hand side is a rational number. But right hand side is a irrational number. This is not possible. And our assumption, what did we assume? That 5 minus root 3 is a rational number. This assumption itself is wrong. So this is not possible, and our assumption that 5 minus root 3 is a rational number is wrong. So that means it's an irrational number, that's it. Therefore 5 minus root 3 is a irrational number. I tried to prove that 5 minus root 3 is a rational number, but I am unable to prove it. That means 5 minus root 3 is an irrational number. Then that completes the proof. Next is example 11. Show that 3 root 2 is irrational. So we already know that root 2 is an irrational number. We already proved it. Okay, root 2 is irrational number. We have already proved it. Now we should prove that 3 root 2 is an irrational number. So what I will do is, as in the previous case, I will assume that this is a rational number. Let 3 root 2 be a rational number. Therefore 3 root 2 is equal to r by s. So so all rational number is in the form of p by q, where p and q are integers and q not equal to 0. Therefore here, since this I have assumed as a rational number, I can equate to r by s, where r and s are integers, and r and s can have some common factor. So I will divide the common factors, and that becomes a by b. For example, 8 by 4 I can write as 2 into 2 into 2. 4 I can write 2 into 2. Now I can divide the common factor. I am left with 2 by 1. So 8 by 4 is equal to 2 by 1. So r and s will have some common factor. So when I will divide them, when I will cancel them, I will get a by b. So 3 root 2 is equal to a by b. Now I will bring this 3 to the right hand side. I will get root 2 is equal to 1 by 3 into a by b. Now you can see that root 2 we already know this is a rational number, sorry, irrational number. Okay, so root 2 is already, we know that it's irrational number, we already proved. Now what is 1 by 3? 1 by 3 is a rational number. 1 by 3 is a rational number, and a by b also is a rational number. So when we multiply two rational number, we get a rational number. So left hand side is a irrational number. But right hand side is a rational number. So this is not possible. Both should be rational number or both should be irrational number. Therefore this is not possible. Because why? Because our assumption itself is wrong. Because our assumption that, what had we assumed? We assumed that root 3 is a rational number, right? So this assumption itself is wrong. This is not possible because our assumption that 3 root 2 is a rational number is wrong. Our assumption itself is wrong. So if our assumption is wrong, then what is right? That root 3 is a irrational number is the right thing. Therefore, sorry, again 3 root 2 is a irrational number, and that completes the proof. The next topic, the next is exercise problem, exercise 8.3, and the first question is prove that root 5 is an irrational number. Prove that root 5 is a irrational number. So here what I will do, I will try to prove that root 5 is a rational number. If I'm not able to prove that root 5 is a rational number, then it is irrational number. Okay, as in the previous examples, what I will do, I'll assume this root 5 is a rational number. Therefore, root 5 is equal to r by s. So all rational number is in the form of p by q, where p and q are integers and q not equal to 0. Therefore, if root 5 is a rational number, it is equal to r by s, where r and s are integers. Okay, and s not equal to 0. Now here r and s will have some common factor which I can cancel. For example, 8 by 4 is equal to 2 into 2 into 2, right? And 4 is 2 into 2. Now I can cancel the common factors like this. So I am left with 2 by 1. 8 by 4 is equal to 2 by 1. Therefore, r and s will have some common factors. And if I cancel the common factors, I am left with a by b. So now a and b have no common factor, because common factor I have cancelled, that's why. So root 5 is equal to a by b. Now I will cross multiply. B into root 5 is equal to a. Now squaring both sides, I will get b square into root 5, the whole square is equal to a square. So b square, root 5 the whole square is just 5, is equal to a square. Now this equation I will take 1 now, and this equation I will take 2. See now, what is the meaning of equation 2? The meaning of equation 2 is 5 is a factor of a square. See, for example, if I write 3 into 2 is equal to 6, so that means 3 is a factor of 6 and 2 is also a factor of 6. If I write 2 into 5 is equal to 10, that means 2 is a factor of 10 and 5 is a factor of 10. So therefore here 5 is a factor of a square. Therefore 5 is a factor of a square. That means 5 is a factor of a also, according to theorem 8.3, which you studied in the previous section. But this contradicts equation 1, which says that a and b have no common factor. See, according to equation 2, 5 is a factor of a, but according to equation 1, a and b has no factor. So 1 and 2 are contradicting each other. So therefore our assumption itself is wrong. What did we assume? That we assumed root 5 is a rational number. So that assumption itself is wrong. That's why we are getting contradictory equations here. Therefore our assumption that root 5 is a rational number is wrong. So therefore root 5 is a irrational number. So I tried to prove that root 5 is a rational number. I am unable to prove it. That means root 5 is a irrational number, and that completes the proof. Exercise 8.3, question number 2, prove that 3 plus 2 root 5 is irrational. So to prove that 3 plus 2 root 5 is irrational, So here also, as in the previous case, I'll assume that 3 plus 2 root 5 is a rational number. Let 3 plus 2 root 5 be a rational number. So I'll assume and I'll try to prove that this is a rational number. If I am unable to prove that this is a rational number, it means that it's an irrational number. So since I have assumed this is a rational number, 3 plus 2 root 5 is equal to r by s, where r and s are integers and s not equal to 0. So all rational number is in the form of p by q, where p and q are integers and q not equal to 0. This is the definition of rational number, right? So here since I have assumed 3 plus 2 root 5 as a rational number, this is equal to r plus s, where r and s are integers. Now r and s will have some common factors which I can cancel. For example, 8 by 4 I can write as 2 into 2 into 2, and 4 I can write as 2 into 2. So I can cancel the common factors like this, and 8 by 4 is ultimately 2 by 1. So similarly, r and s will have common factors. If I cancel them, I'll get a by b. A by b will not have any common factors now. That means a by b, a comma b will have no common factor. Now this is 3 plus 2 root 5. Now I will rearrange this. I will take 3 to the right hand side. So 2 into root 5 is equal to a by b minus 3. I'll get. Again I can write as root 5. Root 5 is equal to a by b minus 3 into 1 by 2. I can write like this. Now you can see 1 by 2 is a rational number. One by 2 is a rational number. A by b also is a rational number. And 3 also is a rational number. So a by b minus 3, rational number minus rational number gives a rational number, and again when it is multiplied by a rational number, we get a rational number. But root 5 is an irrational number. We already proved in the previous problems, in the previous examples. Okay, now left hand side is a irrational number, and right hand side is a rational number. Okay, is a rational number. So this is not possible. This is meaningless. Both should be rational number or both should be irrational number. So this is not possible. So I am framing my own sentence. You also can frame your own sentence in exam. Not necessary to write this way only. Or in textbook they've given some other sentence. Okay, it's always best to frame your own sentence and write. So this is not possible because this is not possible. Okay, because our assumption that, what did we assume? We assumed that root 3 plus 2 root 5 is a rational number. So we assume that this is a rational number. This assumption itself is wrong, because our assumption that 3 plus 2 root 5 is a rational number is wrong. Our assumption itself is wrong. That means what it implies. Therefore, root 3 plus 2 root 5 is an irrational number. So we assumed initially it's a rational number. We assumed 2 plus 3 plus 2 root 5 is a rational number, and we tried to prove it, and we are not able to prove it. That means 3 plus 2 root 5 is an irrational number, and that completes the proof. Exercise 8.3, question number 3, sub question 1. So I should prove that these are irrational numbers. So first one is root 1 by 2. Now I'll try and proceed to prove that this is a rational number. First I'll assume, okay, let 1 by root 2 be a rational number. So therefore 1 by root 2 is equal to r by s. So any rational number is in the form of p by q, where p and q are integers and q not equal to 0, right? So therefore if 1 by root 2 is a rational number, I can equate it to r by s, where r and s are integers and s not equal to 0. Now 8 I can write as 8 by 4 I can write as 2 into 2 into 2, and 4 I can write 2 into 2, and I can cancel the common factors. So I can write 8 by 4 as 2 by 1. So here also r and s will have some common factors which I can cancel, and I can write 1 by root 2 is equal to a by b. Here a and b have no common factor because I have cancelled. Okay, now what I'll do is I'll cross multiply b is equal to a root 2. Now I'll square both sides. So what will I get? B square is equal to a square into root 2 the whole square. So or b is equal to a square into 2. Root 2 the whole square is 2 only. Now what is the meaning of this? B square is equal to a square 2. So what is the meaning of this? That means 2 is a factor of b square. Therefore, for example, I can write 8 is equal to 2 into 2 into 2. That means 2 is a factor of 8. 6 I can write 2 into 3. That means 2 is a factor of 6 and 3 is also a factor of 6. 10 I can write as 2 into 5. That means 10 is a factor of 2 is a factor of 10 and 5 is a factor of 10. So b square is equal to a square into 2 means 2 is a factor of b square. Therefore 2 is a factor of b square. That means 2 is a factor of b also. Okay, this I'll take it as 2 and this I'll take it as 1, but you can check it out. 1 and 2 are contradictory statement. Equation 2 says 2 is a factor of b, but what equation 1 says? A and b have no common factor because we have cancelled all the common factor there. Okay, so this contradicts. Which is contradicting? My equation 2 is contradicting. This contradicts equation 1, which says that a and b have no common factors. One says a and b has no common factor, but 2 says 2 is a factor of b. Okay, therefore why this is happening? Because our assumption itself is wrong. What had we assumed? We had assumed that 1 by root 2 is a rational number. Therefore our assumption that 1 by root 2 is a rational number is wrong. So that means what? That means 1 by root 2 is an irrational number. Therefore 1 by root 2 is an irrational number, and that completes the proof. Exercise 8.3, question number 2, question number 3, sub question 2. Prove that 7 root 5 is a rational number. Okay, 7 root 5. Okay, to prove that 7 to 5 is a irrational number. Sorry, rational number. So what we'll do is we'll assume this as a rational number and we'll try to prove it. If we are not able to prove that this is a rational number, that means it's an irrational number. So let 7 root 5 be a rational number. Therefore 7 root 5 is equal to r by s, where r and s are some integers, where r is not integers and s not equal to 0. So what is a rational number? Rational number is a number which can be expressed in the form of p and q, where both p and q are integers and q not equal to 0. Okay, now r and s will have some common factor which I can cancel. For example, 8 by 4 I can write as 2 into 2 into 2, and 4 I can write 2 into 2. Now these common factors I can cancel, and 8 by 4 is equal to 2 by 1. Similarly here 7 by root 5 is equal to r by s. If I cancel the common factors, I am left with a by b. So, and a by b has no common factor because I have cancelled the common factor. Okay, a and b have no common factor. I'll mark this as 1. Now I'll cross multiply. If I cross multiply, I'll get b into 7 into root 5 is equal to a. Now I'll square both sides. Square both sides. If I square both sides, I'll get b square into 7 square into root 5 the whole square is equal to a square, or b square into 7 square into root 5 the whole square is 5 only is equal to a square. Now what is the meaning of this? I'll mark this as equation 2. So the meaning of the equation 2 is 5 is a factor of a square. Therefore 5 is a factor of a square. So if I write 2 into 5 is equal to 10, what it means? 2 is a factor of 10, 5 is a factor of 10. So similarly 2 into 3, if I write 2 is a factor of 6 and 3 is a factor of 6. So 5 is a factor of a square, and also 5 is a factor of a also, according to theorem 8.3. See, but equation 1 and 2 are contradictory statements. Okay, so I am writing this contradicts. Which is contradicting? My equation 2. Equation 2 is contradicting equation 1. This contradicts equation 1, which says that a and b have no common factors. Equation 2 says that 5 is a factor of a, but equation 1 says a and b have no factors. Therefore our assumption itself is wrong. What is our assumption? Our assumption was 7 root 5 is a rational number. Is wrong. This assumption itself is wrong. That means what is right? That means 7 root 5 is irrational number. I tried proving that 7 root 5 is a rational number, but I failed. That means 7 root 5 is an irrational number. And that completes the proof. Exercise 8.3, question number 3, sub question 3. So we should prove that 6 plus root 2 is a irrational number. Okay. So I'll assume this an rational number, and I'll try to prove it. If I fail to prove it, it means that this is a irrational number. So to prove that this is a irrational number. So let 6 plus root 2 be a rational number. Therefore, if this is a rational number, then I can write as this equal to r by s, where r and s are integers and s not equal to 0. So what is a rational number? Rational numbers are all numbers which can be written in the form of p by q, where p and q both are integers and q not equal to 0. So here 6 plus root 2 I'll equate to r by s, where r and s are integers and s is not equal to 0. Now r and s may have some common factors which I can cancel it out. For example, 8 by 4 I can write as 2 into 2 into 2, and 4 I can write 2 into 2. Now if I cancel like common factors, I am left with 2 by 1. Okay, 8 by 4 is 2 by 1. So here similarly, if I cancel the common factors, I will get a by b. Okay, a and b have no common factor because I have cancelled the common factors. Okay, so 6 plus root 2 is equal to a plus b. Now I will rearrange this one. So root 2 is equal to a by b minus 6. 6 are taken to the right hand side. Now we already know that root 2 is a irrational number. Okay, this is an irrational number. In the previous examples we already proved it. So this is an irrational number, and a by b is a rational number, and minus this 6 also is a rational number. So okay, so rational number in the right hand side, rational number minus rational number is there. Okay, so rational number minus a rational number is a rational number only. Okay, left hand side is irrational number, and right hand side is a rational number. So this is not possible actually. Both should be irrational number or both should be rational number. Okay, so this is not possible because our assumption, what did we assume? We assumed that 6 plus root 2 is a irrational number. Sorry, 6 plus root 2 is a rational number. So this is not possible because our assumption that 6 plus root 2 is a rational number is wrong. Our assumption itself is wrong. So therefore 6 plus root 2 is an irrational number, and that completes this problem and this exercise. The next topic in this chapter is revisiting rational number and their decimal expansions. So in this one we have one theorem, that is theorem 8.5. So what it says, so let x be a rational number whose decimal expansion terminates, then x can be expressed in the form p by q, where p and q are co-prime, and the prime factorization of q is of the form 2 to the power of n into 5 to the power of n, where m and n and m are non-negative integers. So this one explanation, I'll give some practical example and I'll explain you. Now 0.375, this is a rational number. Okay, so what is a rational number? Rational number is in the form of p by q, and where p and q are integers and q naught is equal to 0. So rational number, the decimal expansion of a rational number terminates. Okay, and 0.375 is a rational number because decimal is terminating. So now this one I can write as 375 by 1000. Okay, now I can this again I can write as 375 by 10 power of 3. Now again this one I can write as 375 by, now 2 into 5 is 10, 2 5s are 10, the whole cube. Now this one again I can write as 375 by 2 to the power of 3 and 5 to the power of 3. Now this is what the theorem says. Now decimal expansion, see now I have written this in the form of p by q. Okay, p is 375, q is 1000. Also q can be expressed in the form of 2 power of n, 5 power of n. Ultimately now q I have expressed as 2 to the power of 3 into 5 to the power of 3. Now I'll give you another example. Now consider another fraction, 0, another decimal which is terminating. Now this is a rational number. Now this I can write as 104 by 1000. Now you can 10 by 1000. Okay, now see this is in the form of p by q. Now denominator I can write in the form of 2 power of n, 5 into 5 power of n, that is 104. I'll write as it is. Now 10,000, this is 10 power of 3, so 104. So 10 is 2 into 5, 2 power of 3, so this is 104 by 2 power of 3 into 5 power of 3. So as stated in this statement of this theorem, I have expressed decimal expansion in the form of p and q, and also q I have expressed in the form of 2 power of n into 5 power of m. The next topic is theorem 8.6. So theorem 8.6 says, let x is equal to p by q be a rational number such that the prime factorization of q is of the form of 2 power of n, 5 power of m, where m and n and m are non-negative integers. Then x has a decimal expansion which terminates. So I'll explain this by giving you one example. Now consider 7 by 80. So this is a rational number. This is in the form of p by q. Okay, this is in the form of p by q. Now I'll factorize numerator and denominator. So 7 is a prime number which cannot be factorized. Now 80 I can factorize 80. 2, it's divisible by 2. 2 4s are 8, 2 0s are 0. Then 2 2s are 4, 2 0s are 0. 2 2 tens are 20. Now 2 fives are 10. So this I can write as 2 into 2 into 2 into 2 into 5. So this again now I can write as 7. So 2 multiplied by 4 times, that means 2 to the power of 4 into 5. Okay. So in the denominator of right hand side we have 2 to the power of 4, but power of 5 is just 1. Okay. So 7 by 2 power of 4 into 5. So 5 means 5 power of 1. So I want to make this 5 power 1 as 5 power of 4. So what will I do? I will multiply and divide by 5 power of 3 into 5 power of 3. So what will I get is 7 into 5 power of 3 divided by 2 to the power of 4 into 5 power of 1 plus 3 I will get. So this is equal to 7 into 5 power of 3 divided by 2 power of 4 into 5 power of 4. So this again now I can write as 7 into 5 power of 3 divided by, now in the denominator I can write as 2 into 5 power of 4. So this is equal to 7 into 5 power of 3 divided by, so this is 10 power of 4 I will get. 2 5s are 10 to the power of 4. So numerator is actually 5 into 5 into 5 into 7 I will get 875. 875 by, in the denominator 10 power of 4 means 1 followed by 4 zeros. So now if I divide this one I will get 0.0875. Okay, this is what the theorem says. So given a rational number we can express in decimal which terminates. And what is the condition? If x is equal to p by q be a rational number such that the prime factorization of q is of the form of 2 to the power of m, 5 to the power of m, where n m are non-negative integers, then x has a decimal expansion which terminates. So 7 by 80 we got 7 by 2 to the power of 4 into 5 power of 1. So ultimately after simplification we reduce that 7 by 80 into decimal which is terminating. So this is 0.0875 and the decimal terminates, and that finishes the theorem. So there is no proof as such for this theorem. We can just check out some practical examples. Okay. The next topic is theorem number 8.7. So what it says, so let x be p by q, a rational number such that the prime factorization of q is not of the form of 2 to the power of n, 5 to the power of m, where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating, that is recurring. So I'll give one example for this one. Consider a rational number p by q. So consider 1 by 7. So this is in the form of p by q. Okay, where 1 is an integer and 7 is an integer, and 7, the denominator is not equal to 0. So but now if we factorize, what it will be? Factors of 1 is 1 only. So factors of 7 is also 1 and 7. But the denominator we are not able to express as 2 power of n into 5 power of m. So in this case, when we divide 1 by 7, so what we get is, we get recurring decimal. Okay, when we divide by 7, we get 0.142857 1. Again it will recur. Okay, that means these digits, it keeps on repeating. So why? Because we are not able to express the denominator in the form of 2 power of n into 5 power of m, and that completes this theorem. There's no proof for it, it's just an explanation. So we should check some practical examples, that's it. And now we'll go and solve some exercise problems. Exercise 8.4, question number 1. Without actually performing long division, state whether the following rational numbers will have terminating decimal expansion or a non-terminating repeating decimal expansion. So here what we should do is, there are rational numbers here, we should check the denominator. If the denominator can be expressed in the form of, see here you have studied in theorem 8.4, if the denominator, if we can express, see the cursor, if we can express in the form of 2 power of n into 5 power of m, where n and m are non-negative integers, then it will be, then the decimal expansion will terminate. If we can't express in the form of 2 power of n into 5 power of m, then the decimal expansion will be non-terminating repeating. Okay, so first sub question is 13 by 3125. So we'll factorize both numerator and denominator. Numerator is a prime number, it cannot be factorized. So denominator we can factorize. So it's divisible by 3, divisible by 5. So 5 6 are 30, 5 2 are 10, 5 5 are 25, 5 1 are 5, 5 2 are 10, 5 5 are 25. Then again 5 2 are 10, 5 5 are 25, 5 5 are 25, 5 1 are 5. So denominator I can write as 5 into 5 into 5 into 5, 1 2 3 4 5, 5 5s are there. So this I can write as 13 by 5 power of 5. Now you can see this I can express as 13 by, I can write 5 power of 5 as 1 into 5 power of 5. Now again 13 I can write as 13 by 1 I can write as 2 power of 0, 2 power of 0 into 5 power of 5. So now the denominator is of the form 2 power of n into 5 power of m, and where n and m are non-negative integers. Therefore the decimal expansion of, therefore the decimal expansion of 13 by 3125 is terminating. So also in question number 2 they are told here, write down the decimal expansion of those rational numbers in question 1 above which have terminating decimal expansion. So if it is terminating, we should write down the decimal value also. So for that we need to divide. So 13, if I divide by 3125, so 13 is not divisible, therefore I put one decimal point and take 0. Still it is not divisible. Now I'll put 1 0 and put 1 0. Still it is not divisible. Again I'll put 1 0. Now 3125 into 4 is 12,500 I'll get. So 500 is remaining. Now I'll put one more 0. Then 3125 into 1 is 3125. Now I'll get 5781. Now if I'll put 0, now 3125 into 6 I'll get 18,750. Okay, therefore 13 by 3125 is equal to 0.00416. The second sub question it is 17 by 8. 17 cannot be factorized, it's a prime number. So 8 I can factorize. 2 4s are 8, 2 2s are 4, 2 1s are 2. So 2 into 2 into 2. So this is equal to 17 into 2 power of 3. So this I can write as 17 by 2 power of 3 into 1. Again this I can write as 17 by 2 power of 3 into 5 power of 0. 5 power of 0 is 1. Okay. Therefore, the denominator is of the form 2 power of n into 5 power of m, where n is 3 and m is 0. Both are non-negative integers. Therefore, 17 by 8 is terminating. So to find the terminating expansion, I need to divide. So 17 divided by 8. 8 2s are 16. So 1 is remaining. It is not divisible. Put one decimal point and take 0. 8 1s are 8. Now 2 is not divisible. I'll put 1 0. Now 8 2s are 16. Now 4 is there. I'll put 1 0. Now 8 5s are 40. Therefore 17 by 8 is equal to 2.125. So third sub question, it is 64 by 455. So 64 can be factorized. So 64 divided by 2. 2 32s are 64. Then half of 32 is 16. Then half of 16 is 8. Half of 8 is 4. Half of 4 is 2. Then 2 ones are 2. So 2 into 2, 1 2 3 4 5 6. 2 into 2 into 2 into 2 into 2 divided by 455. 455 is, it is said divisible by 5. 5 9s are 45, 5 1s are 5. Then 7 1s are 7, 7 3s are 21. 13 is a prime number, 13 1s are 13. So here 5 into 7 into 13. So here 2 power of 6 by 5 power of 1 into 7 power of 1 into 13 power of 1. So the denominator is not in the form of, the denominator is not in the form of 2 power of n to 5 power of m. Therefore, the decimal expansion of this number is non-terminating repeating. Therefore, 64 by 454 is non-terminating repeating. Fourth sub question, it is 15 by 1600. So 15 when factorized, 5 3s are 15. So this is 3 into 5. 1600 when factorized, so it is divisible by 5. 5 3s are 15, 5 2s are 10, 5 0s are 0. then 5 5 6 are 30, 5 4 are 20. Now divided by 2, half of 64 is 32, half of 32 is 16, half of 16 is 8, then 4, then 2, 2 ones are 2. Now this I can write as 2, 1 2 3 4 5 6, 1 2 3 4 5 6 into 5 into 5 into 5 into 5. So here I can cancel the common factors. Okay, 5 will get cancelled. So here 3 by 2 power of 6, 1 2 3 4 5 6, 6 into 5 power of 1. So the denominator is of the form 2 power of n 5 power of m, where m and n are non-negative integers, where n and m are non-negative integers. Therefore 15 by 6 is terminating. So we'll evaluate that one. So 15 when divided by 1600, so it's not divisible, so I'll take one decimal, put 1 0. Now also it's not divisible, again one more 0 I'll take, and one more 0 I'll take. Now 1600 into 9 is 14400, so I'll get 600. I'll take 1 0 now. Now 1600 into 3 is 4800. I'll get 1200 remaining. Now not divisible, I'll put one more 0. Now into 7 I'll get 11200, so 800 will be remaining. I'll put on 0. Now 16 into 5, 1600 into 5 is 8000. So 15 by 1600 is 0.009375. The next sub question is 5. It's 29 by 343. 29 is a prime number, can't be factorized. Now 343, it is divisible by 7. 7 4s are 28, 7 9s are 63, 7 7s are 49, 7 1s are 7. So this is 7 into 7 into 7. So this is equal to 29 into 7 power of 3. So the denominator is not of the form 2 power of n into 5 power of m, where n and m are non-negative integers. Apart from 2 and 5, the factors of 344 is 7. So therefore 2 power of 9 into 343 is non-terminating repeating, or simply recurring. So the next sub question is 23 by 2 power of 3 into 5 power of 2. So clearly in the question only answer is there. The denominator is in the form of 2 power of n into 5 power of m, where n and m are non-negative integers. What is the value of n? Value of n is 3, value of m is 2. Okay, therefore 23 by 2 power of 3 into 5 power of 2 is terminating. That means the decimal expansion is terminating. Okay. So let us evaluate. So 23 divided by, so what is 2 power of 3? So 2 power of 3 into 5 power of 2 is equal to 2 power of 3 is 8. 2 into 2 into 2, 8. 8. 5 power of 2 is 5 5 is 25. 25 into 8 is 200 I will get. So 23 divided by 200. So not divisible. So I'll take one decimal point and put on 0. So 1s are 200, 1s are 200. Now 30 is remaining. I'll put on 0. Now 200 1s are 200. Now 1 is remaining. 100 is remaining. Now I'll put on 0. Now if I multiply by 5, 200 into 5 is 1000. Divisible. Therefore 23 by 2 power of 3 into 5 power of 2 is equal to 0.115. Sub question 7. So given rational number is 129 by 2 power of 2 into 5 power of 7 into 7 power of 5. So this is very simple. The denominator before that I'll try to I'll factorize 129 also, the numerator, and I'll see if any common factors are can be cancelled or not. So the 129 is divisible by 3. 3 4s are 12. 3 3s are 9. 43 is a prime number. So this is 3 into 43 by 2 power of 2 into 5 power of 7 into 7 power of 5. So there is no common factor which I can cancel. Therefore the denominator is not in the form of 2 power of n into 5 power of m, where n and m are non-negative integers. Therefore 129 by 2 power of 2, 5 power of 7 to 7 power of 5 is non-terminating repeating. Non-terminating repeating. That means it is recurring. Okay. The next sub question is question 8. So 6 by 15. So this is a very simple one. Factors of 6 is 2 3s are 2 and 3. Okay. 15. Factors of 15 is 5 3s are 15. Then 3 1s are 3. So this is 2 into 3. Here it is 3 into 5. So this and this I can cancel. So I'll be left with 2 by 5. 5 means 5 power of 1. So this I can write as 2 by 5 power of 1. Again 2 by 5 power of 1 I can write as 2 by 1 into 5 power of 1. So this I can write again 2 power of 0 is 1 into 5 power of 1. Okay. Now clearly the denominator is in the form of 2 power of n into 5 power of m, where n and m are non-negative integers. Okay. Therefore 6 by 15 is terminating. That means the decimal part will be terminating. Now to evaluate that, I will divide now 6 divided by 15, so it is not divisible. So I'll put one decimal point and take 1 0. Now 15 4s are 60, therefore 6 by 15 is equal to 0.4. Okay, next question, sub question is question 9. So given is 35 by 50, so 35 by 50, if I factorize 35, 7 5s are 35, then factorizing 50, 5 10s are 50, then 5 2s are 10, 2 1s are 2, so this is equal to 7 into 5, 7 5s are 35, this is 2 into 5 into 5, so this I can cancel. Now I'm left with 7 by 2 into 2 means 2 power of 1, okay, then 5 means 5 power of 1, so the denominator is of the form 2 power of n into 5 power of m, where here n is 1 and m also is 1, therefore 35 by 50 is terminating. So I can, to evaluate 35 by 50, I can divide 35 by 50. Also I can divide it by same thing I can do by dividing 7 by 10 also I can do. Okay, now here 35 divided by 50, it's not divisible, so I'll put one point and put one 0. Now 7 5 is 35, so 350. See here, some common factor got divided and I got 7 by 10. 7 by 10 if you divide, then also I should get the same answer. So I will put one decimal point, put on 0, 10 7s are 70. So 0.7 is the answer. Therefore 35 by 50 is equal to 0.7. The last sub question is 10. So double 7 by 210. So double 7, if I factorize 7 1s are 7, 7 1s are 7. So this is equal to 7 into 11. So 210, 210, 2 1s are 2, 2 0, 2 5s are 10. Then 5 2s are 10, 5 1s are 5. Then 7 3s are 21, 3 1s are 3. So this is 2 into 3 into 5 into 7. So 7 7 I can cancel, so I'll be left with 11 by 2 into 3 into 5. So this is non-terminating. The denominator is not in the form of 2 power of n into 5 power of m. So apart from 2 and 5 as the factor, even 3 is there. Therefore 77 by 210 is non-terminating repeating. And that completes question number 1. And question number 2 I already solved. Write down the decimal expansion of those rational number in question 1 above which have terminating decimal expansion. This already along with question 1 I have done it. Wherever the rational number was terminating, I evaluated and I have written the decimal expansion. Exercise 8.4, question number 3. The following real numbers have decimal expansion as given below. In each case, decide whether they are rational or not. If they are rational and of the form of P and Q, what can you say about the prime factor of Q? So first sub question is 43.123456789. So in this decimal, the decimal is terminating, so that means it is a rational number, and the denominator, the factors of the denominator are 2 and 5. So I am writing decimal is terminating, therefore it is a rational number. And also now what are the, if it is rational number and the decimal is terminating, the denominator, okay, what can about the prime factor of Q? The denominator is of the form of 2 power of n into 5 power of m. That means 2 and 5 are the factors of the denominator. And the second sub question, the given question is 0.1201200, then 12000, then 1240, and it is recurring. Therefore decimal is non-terminating recurring, non-terminating repeating, okay, repeating. Therefore it is a irrational number, okay, it is a irrational number, irrational number. So now what can I say about the denominator? So here we can't say anything about the denominator, because this is an irrational number, therefore it won't be in the form of P and Q, okay. And the last one, the last is 43.1234567 and 1234567 and okay 9 also is there. This is recurring. So since this is recurring, this is a rational number, okay, decimal is non-terminating recurring, therefore it is a rational number, and the denominator is not in the form of 2 power of n, 5 power of m. Therefore the denominator is not in the form of 2 power of n, 5 power of m. So that means it has prime factor other than 2 and 5, okay. And here in the first case the prime factors are 2 and 5, factors other than 2 and 5. And that completes this question and this chapter.